My name is Melosh. I'm from Purdue University, and my major interest right now is impact cratering. And so that's where I'm going to get started. And in preparing this talk for today, I was thinking back to a number of conferences that within our tiny community of people working on impact craters has been important. We arranged in the last couple of years 2 conferences that we call Bridging the Gap conferences. Bridging the Gap 1 and 2, and maybe there will be a 3 coming up next year. The reason for those conferences was because there's a widening gap between people who create models of impact craters and people who actually observe them in the field or use impacts in their research in one way or another. The 2 communities, almost 2 cultures, don't understand each other very well. And so I've given a couple of talks at these conferences on what modeling is and what it can do for you to try to let the modelers know what it is we need to know about impact craters, what we can know from modeling. And in putting together the talk today, I decided, even though I'm going to be talking to the choir here, I will mention some of the elementary things about modeling, because these are the things that I have found that modelers or that non-modelers do not understand. And I think we need to keep that in mind in an enterprise that involves geomathematics, is that the community of users outside our community often don't understand what seem to be some of the really basic things. And so I'm going to emphasize those just to give you an idea of what it is that people don't understand. And these are tried and tested through a couple of conferences. I think I've gotten an idea of just what it is people don't understand, at least some of the things. So let me go forward and first introduce my subject. That's impact cratering. Oh, does somebody have a pointer? I didn't bring one. Oh, okay. Well, I'll use the analog version then. Okay, we now believe that our solar system and other solar systems, which we're beginning to observe, and I should say parenthetically, we have now seen the result of a planetary scale impact in another solar system, a system called euphoniously HD 172555, about 30 light years from here. At any rate, our planetary system, we believe, started with a formation of our sun, a cloud of gas and dust. The dust condensed into planetesimals, a term, by the way, that was coined here in Chicago by Thomas Crowder Chamberlain at the University of Chicago in around 1909. It was his idea that this is the way planets formed, and he was very prescient about that. At any rate, as the planetesimals grew to be bigger and more gravitationally deflecting, impact velocities increased, planets grew in size, the large impacts caused extensive melting. Planets, we believe, were born with an inverse temperature distribution, cold inside from their low velocity beginnings and hot outside, presenting a challenge to geodynamicists as to how the inversion took place to put the heat in the middle and the coolness on the outside. Collisions of all scales occurred, culminating in some giant impacts. We now believe, well, at least it's plausible, that the planetary dichotomy, crustal thickness dichotomy on Mars is the result of a very large impact with an object about 600 kilometers in diameter shortly after the formation of Mars, and that our own moon was probably formed by the impact of a Mars-sized object that collided with the Earth and blasted out a cloud of hot gas and dust that condensed into the moon. Although there are some problems with this, and in other lectures I talk more about this. There are some mysteries with this there's some mysteries with this whole scenario that we have yet to resolve, but we'll probably do it by modeling. Okay, thank you. That will help. In more recent times, we believe the collision of a small asteroid, about 12 kilometers in diameter, with the Earth, extinguished the dinosaurs and cleared the decks for our ancestors to evolve and for humans to take over the Earth. Exactly what happened during that event is something that we're trying to clarify. We have evidence, we have the debris that was ejected, but there's still a lot missing, and that's one of the things computer modeling can help us with, is to try to understand what are the effects of an impact of this scale, something that's completely unprecedented in our own times, and frankly, we probably don't want to do experiments on this scale of collision anyway. How do we study these impacts? Well, on the small scale, we can study high velocity collisions in the laboratory. This image here, which may be difficult to interpret in the beginning, what you see there is a vacuum tank, the ladder for scale. It's about 2 meters in diameter, 3 meters high. This is at the Ames Research Laboratory in California, and the Y-shaped beam carries a two-stage light gas gun that can fire projectiles at about 6 kilometers per second, roughly the highest speed possible for this kind of acceleration facility. Projectiles can be up to a couple of grams at this high velocity. This facility has been in use continuously since it was constructed in the 1960s and has yielded a great deal of information on high velocity impacts. Although the velocity is not as high as typical solar system impact velocities by a factor of about 3, and of course the scale of the collisions is very small. Just to give you a feel for, oh, let's see, how do I initiate this? Huh? Oh, okay. Okay, just to give you a feel for what one of these impacts looks like, this is a block of rock. This is a block of rock about 20 centimeters across that we, whoops, okay, that we impacted with the Ames gun. This is inside that vacuum tank. And you can get a feel for what an impact does. It disintegrated the block. Now think about what happened in the early solar system when collisions occurred. How about these planetesimals? Were they fragmented? How much gravity do they need to hold them together? We can up the scale a little bit, a couple orders of magnitude. If we go, instead of to impacts, nuclear explosions, thanks to the DOD. We've got a couple of craters. On the left is the Sedan crater, which, or the Sedan explosion, which made a crater about 360 meters in diameter. You can visit the Nevada test site today and go and visit it. It's the frequent destination of Boy Scout groups and church groups and so on to go and see this crater in alluvium. Schooner crater on the right looks much more like meteor crater, except small. It's about 300 meters in diameter, and you can't go see that. It's now been closed to visits of any kind, except for the people in Area 51. So what do we want to know about impacts? We want to know a couple things. It's a long, long list, but when is a planetesimal disrupted by an impact, and when does it grow? How big does it have to be? When does self-gravity trump the energy of the impact? How much melt is produced, and how is it distributed? Does it deepen the target? Is it splattered over the surface? How much material is injected into orbit by a giant impact? Where does it go? How much of the material that gets into orbit is projectile? How much comes from the Earth? And what are the climatic effects of large impacts? And how do they really cause a global extinction? How did the oceanic extinctions occur as opposed to the land extinctions? Those are the kinds of questions we want to answer. And lacking the ability to do experimental work, what do? How do we answer these questions? How do we make any progress in understanding how our solar system came to be? Well, the modern answer, as you know, is computer modeling. What we can do with computer models is we can expand or contract the size scale from experimental studies. We can study conditions beyond the reach of experiment. We can increase the velocity in a computer calculation. And we can add physics that can't be reproduced experimentally. For example, in the collision that produced the moon, we can include self-gravity of the material that is splattered out, not something you can do in an experimental study. Self-gravity is unimportant in the Ames gun experiment, and it will remain important, just unless we, I suppose, use neutron star matter or something, but again, a little implausible. The other thing that we can do is verify the physics. We can do computer models of processes, observe the results, and if the results do not match observations, that's a clue that we're missing something. Of course, it may also be a clue that there's a bug in the computer code, and you need to be judicious about just which is which, and when you stop hunting for a computer bug and start to say, I need to put in some new process. Models have to be tested, and that's something that my modelers often forget. You need to do models of the very experiments that we can do. That is, if we have a laboratory scale model, we need to take our computer models and reproduce them and make sure that the computer code gives the same results of the known experiment. Models have to be compared with observations. And I'm going to talk a little bit about a fine lesson in that almost nobody knows about. Is a Department of Defense, let's call it an experiment that lasted 30 years that told us a lot about the value of modeling over data that was falsified. One thing that we have to be aware of as modelers is just because a computer image looks good doesn't mean it's real. And that's something that when I've said it in front of my Los Alamos colleagues, almost always gets them angry and grumble at the coffee hour afterwards. But it is absolutely true. A lot of models that are run look beautiful, but may have absolutely nothing to do with reality. And so you have to approach these things with a lot of skepticism. I will. I'm coming to that. Okay, but, and this is for the people who are not modelers. Probably nobody in this room, but, you know, folks who are not modelers have to know these things, and they often don't. You first have to decide what you want to know. Too many people come to me and say, well, let's do a model of something. And they'll say, well, why do you want to do that? And they say, well, I don't know, just do a model. You know, as I presume, make a pretty picture or a movie or something like that. That's not why we do modeling. So we have to decide, what are we going to model? Are we modeling a whole planet? Are we modeling an individual rock that we're trying to learn more about? You have to decide on the scale before you can begin any modeling task. Again, one of these things that sounds obvious, but I have so many times run into people who did not appreciate this. And I think that as a community of mathematical geophysicists, we have to appreciate what is it that the outside community doesn't really understand. So the other important concept that many people don't understand is resolution. All models discretize a real object into cells, which are internally uniform, and are, you know, the internal structure of each cell is averaged on some resolution scale. We could imagine starting with some complex geologic system. This is you know, an illustration of what happens at the KT boundary, a fine circus. We discretize the object of interest into small elements, which are uniform and therefore approximations to the actual complex structure. But we do that hoping to at least extract the relevant properties for the problem that we want to answer. That is, we don't want to know whether this beast had appendicitis or not. We perhaps want to know what size crater it will make, and therefore we don't need to know the internal details. The number of cells or elements depends upon the desired resolution. If n is the number of cells per linear size in 1D, the number is the length scale divided by the resolution. For 2D, it's n squared. For 3D, it's n cubed. And I'm putting us in because a lot of people think the 3D modeling is easy. We're doing that now. We've been doing 3D models for a few years at much lower resolution than we can do 2D models, but it's not, as most of you in the room know, not that easy. Number of cells translates into need for storage, and that goes like the first, second, or third power of the number of linear cells. And then I give an example for 1,000 cells horizontally, say, what kind of storage you need, and it grows rapidly with the size of the problem. The amount of computer storage depends upon the resolution, and you can't do a planet and a rock in the same calculation. Even with multi-terabyte storage, there are limits, as again everybody knows here. The runtime depends on the duration of time. Runtime is controlled, at least in these explicit impact models where the main limitation is the speed of sound. It's controlled by this time that sound takes to cross the smallest cell in the problem. And that grows even faster with the number of dimensions, because as the cell size shrinks, the runtime increases. And so for different sizes, you can get 5 seconds runtime for 2D, the same thing, an hour for 3D, it might take a month. Again, not widely appreciated by people outside the community. In older calculations, this is the first impact calculation as far as I can tell. This is a 2D simulation of an impact that was commissioned by NASA because of the fear that meteor impacts would be the main hazard in flying in space. It was wrong for interesting reasons, but nevertheless it motivated some of the first impact calculations. In this calculation, this pushed the computer resources at the time. This is a 20 by 20 mesh, and in 2 dimensions, and that was proudly displayed by the authors of this study to show what a huge calculation they could solve. Nowadays, of course, we don't even bother to show the mesh because it would be too fine. I persuaded some of my colleagues to show the mesh. This is actually a 3D simulation, and you can see the mesh is so fine that it would be ridiculous to show it in any normal calculation, but it's always there. And you have to keep what that resolution is in mind and make sure that your calculation is resolved. And okay, one of the things that, again, a lot of people don't appreciate, and including modelers, and I've seen a number of papers recently that do not respect this. It sounds obvious, but your results should not depend upon the resolution. That is, if you double the resolution, your results shouldn't change. There are even algorithms that don't have that property. You should not use those algorithms. But it turns out, for example, the origin of the moon calculations that you may have seen on documentaries or at meetings, these are SPH calculations that Robin Canup has been doing. They are not resolved in the sense that as the resolution of the SPH method increases, the results change. And we are not yet resolved in that particular calculation. But of course, the calculation is at the limit of computer resources at the present time. Okay, there are 2 basic types of computer hydrocode simulations, each with advantages and disadvantages. There's the Lagrangian type calculation. Okay, that something got displaced there, but at any rate, in which the material follows the cells. Interfaces are well resolved, but mesh distortion can very quickly end the calculation. When it becomes too distorted, the calculation can no longer proceed. In the Eulerian simulation, material flows through the static mesh. You blur material interfaces. Cells contain mixtures of material, and one has to develop different ways of handling that. There are dozens of ways of doing it, some more successful than others. And the mesh has to be large enough to contain the entire evolution, although adaptive meshes and moving meshes are now being developed. There are lots and lots of refinements on these basic types. The smooth particle hydrodynamics is currently very popular. It suffers from an inherent low resolution that many users know about, but people who aren't users don't, because nobody has ever published, as far as I know, of the resolution of, say, standard Eulerian methods to SPH in a way that anybody could find. I've done that calculation or comparison myself years ago with Willie Benz. The results were so horrifying for SPH that he didn't even want to publish it. But SPH is inherently very low resolution, although easy to code. Adaptive mesh resolution is, or adaptive mesh refinement is the current answer to problems with the mesh. There are some problems with that that are not particularly well understood. There's something I call numerical surface tension that develops and can add unphysical motions. If you start out with a plain sheet and let AMR, in a naive AMR, go to work, the sheet will rapidly form up into globules as if there were surface tension. So it's sort of a numerical artifact that seems to be endemic to AMR. So something you have to be careful of, especially since it's being used by astrophysicists to study coagulation in the early universe. Okay, hydrocode modeling stands on two basic pillars. One is mechanics, F equals ma, which is really all these codes are. They're typically explicit. And thermodynamics, you need an equation of state, and that's a little bit more serious. Physics, you need to know the relation between the pressure, internal energy, and density to make these codes work. Let me not belabor this. You probably all understand this, how you go forward from one cell to another. Equations of state in current use, well, the simplest ones are perfect gas. You can add levels of complication. Stiffened gas, a Gruneisen equation that relates the pressure to internal energy. Tillotson equation, which is a algebraic equation that doesn't have phase transformations but is created for impact calculations. And then various sesame tables are tabular equation of state. Anios is an analytical approximation to the equation of state, and so on. There are some modern ones like Panda that has literally thousands of input parameters that does a very good job describing materials, but there are not many materials for which we have parameter sets. Beyond equations of state, of just the pressure, we also need to know something about the rest of the stress tensor, whether material is elastic, viscous, what its strength is, the fracture mechanics, porosity, dilatancy that may occur during compression or shear, and then we have problems of how to treat mixed materials. All these things are subject right now to the pretty active study. So the Pacific Craters problem. What was this? This is thanks to the DoD, which did not intentionally do this. In 1958, there were a number of nuclear explosions on Eniwetok Atoll, big hydrogen bombs, 8 megatons and so on, that produced craters. I apologize, this probably doesn't show up very well, but these come out of a couple of USGS reports on the craters. The craters were made in 1958. In 1957, I attended my first conference on cratering, took place in Flagstaff. There were a lot of military people there because craters are of interest not just to scientists, but the main question that was being asked at the time at that conference by the military community is, what about the Pacific craters? What's going on with the Pacific craters? The reason is, if you were able to read the contours on this, you would see that these craters are very shallow and broad. Now, if you use the standard crater scaling laws that had been established before, or if you do hydrocode calculations, at the time the DoD, people, Los Alamos and Lawrence Livermore, were the main modelers, they predicted that the craters that would be formed were this big. That was the size of the craters. And in this one, let's see, yeah, this big. Instead, the craters are much larger by factors of about 5, and they're much shallower than was predicted. Well, the model and the observations disagreed. So what do the modelers do? Yeah, everybody knows you mess some physics. And so the communities doing this kind of modeling began to put in more physics. Well, maybe it was because these are thermonuclear explosions. Maybe it was the pressure of the gamma rays on the surface of these high-yield nuclear weapons that pushed the material out. Well, that didn't work. Well, maybe it was the constitutive relation. Let's do something about that. Well, that didn't work. Years rolled on. It began to be a major problem that nobody could reproduce these craters. The first meeting I had with some Russian geoscientists who worked in the cratering field was, "Comrade, do you understand the Pacific craters?" The Russians were obviously very concerned as well as to what is going on. These thermonuclear explosions did something that could not be reproduced. For 30 years, there was this great uncertainty about what the heck was going on. Now, when I first talked to people about this, I had been interested in lunar craters and been studying the collapse of lunar craters due to a process called slumping. Something that requires actually some new physics. The slumping doesn't occur unless a strange sort of weakening has occurred that I think is due to the vibrations caused by the excavation. And I naively said, well, what about slumping? You made a big crater. This is in coral rock. It's 50% porous. It's coral connected together with water in between. Why didn't the shock wave bust up the coral rock and have it just slump in and fill up the craters? I mean, in fact, the volume of the Pacific craters is almost exactly the volume that you predict from numerical calculation. And I was told that that was not possible to consider because a certain program manager, whom I could name but I probably won't, within the Department of Defense had decided that it was not slumping, that didn't occur. And pretty soon he was staking his career and his credibility within the DoD on the idea that slumping didn't occur. So this process was the one process that was off the table for all the DoD modelers. Slumping could not be considered. And we went on for 30 years, this being the major uncertainty in the Pacific craters. Hundreds of millions of dollars were spent on simulations, on modeling exercises, all sorts of things to try to explain these to no avail until this certain person retired and the Navy sent in submersibles and they found the rim of the crater inside that bowl exactly where it was expected by all the previous modeling exercises. So I take this, although you could take this rather negatively, I take this as a wonderful vindication of the integrity of people doing modeling, that in spite of being fed false data and it being insisted that this process that it actually explained it, slumping, there's no doubt they've now, you can see from this plot, they've done boreholes and so on. There's absolutely no doubt that the slumping occurred. But the modeling community, having been fed false data, was unable to come up with an explanation for these observations. Yeah. Sorry, I can't hear.
What is that profile from? Is it a refraction profile?
This is from the USGS report on the Pacific craters. Over the USGS got involved, and this is in the open literature. I could send you a PDF of the report if you really would like. And this is a little bit ratty, but at any rate, there are big fold-out maps of the seismic reflection profiles. So I count this as a great success for modelers, that at least honest modelers weren't able to get the wrong answer, in spite of a lot of prodding.
There are ways of explaining the same result.
Yeah. I agree. Sometimes modelers are able to match things that are false. Yeah. Well, yes, I have to be very skeptical of models as well, but at least there's sometimes, like this one, when everything works the way it should be. Yeah, somebody ought to collect these or something like that for, good reading for modelers. Anyway, the basic lesson from all of this is that modeling itself is a pretty useless exercise. It's just making pictures. That observation, experiments, and modeling have to be done all together, and there has to be good communication between all disciplines if this is going to be anything other than movie making like Hollywood does. And I want to end up with just a couple of demonstrations of models. If I know it's getting late, if I'm out of time, I can skip this. But if nobody drags me off, I'll go ahead. Okay. Okay. Well, these are three different models of some real situations. The first is Chesapeake Bay crater. There's an impact crater that is about, well, it's variously cited as between 20 and 80 kilometers in diameter in the Chesapeake Bay. And it was this crater about 34 million years ago that caused the distinctive convergence of different rivers in the Chesapeake region that we recognize today. The crater was discovered only long after the area was mapped geologically due to a funny breccia, the Exmoor breccia, that was slowly recognized to be of impact origin. But it's a very odd crater, because this cross-section on the right shows there's a deep inner crater. That's really what, for most crater modelers, that's what the true crater is, and that it's that crater, the inner one, that gives you the size of the projectile, which is about 2 kilometers in diameter, we think now. But there's this outer zone of disturbance that's about 80 kilometers in diameter that appears to be disturbed sediments. And the lithology of the area is there's granitic rock, Grenville Age basement, with a lot of marine sediments overlying it. It's actually somewhat asymmetric, something we're doing now with 3D. But the question is, can we model that? We've now got boreholes in a couple of different places. We've got good seismic maps of it. Can we make a decent model of what happens? And we're now getting good enough that we can do a pretty good job. See, the impact occurs. The basement rock is uplifted. This is part of this magic that's going on. It's fluidized briefly. The sediments are cleared away. And then because they're loose, they flow back and fill up the crater bowl. And if we compare the seismic sections with the model, they are almost indistinguishable. In some of the papers that we published lately, we put one next to the other. Actually, this is being done not by us, the modelers, but by the people who created the seismic sections. They're amazed at how close the model gets to reproducing the observation. This depends upon getting the constitutive properties right, that is the flow properties of the sediments versus the basement rock. Yes, yeah. The slumping is what creates the central peak in the basement rock. Most craters do not have this great expansion. It sort of looks like an inverted sombrero, the crater. That's not unique on the Earth, but it is unusual. There are one or two other craters like Samantian with the same structure, and it's because of water-saturated sediments that you get this great expansion of the near surface area. And the Chicxulub crater, another big crater, about 170 kilometers in diameter. At least that's the collapse diameter. It has a peak ring that is toward the center, a high in both gravity and topography, and a small mantle uplift. Again, something that we cannot reproduce in laboratory experiments on craters. Can we do it numerically? And the answer is, of course, yes. Now, it's taken years to get to this place. Here we have sediments that are more stiff. These are anhydrites that are pretty stiff over granitic basement and then mantle material down here. Notice the scale of kilometers out 0 to 100 kilometers. And here we go. Here's our impact. We get uplift in the center, collapse, and you can see a zone in which the rim sediments step down. They're overturned, something we have now validated with drilling. We get the peak ring, which you can't really see very well in this image. And we get a small mantle uplift that agrees pretty well with the observed mantle uplifts. So again, the modeling seems to contain most of the relevant physics, although some of the physics, for example, the fluidization due to vibrations, is unique to these models. This is not something we have observed in small craters. It only occurs in big craters, bigger than about 3 to 5 kilometers on the Earth. So, even the biggest nuclear explosions haven't done that yet. And my last example is the South Pole Aitken Basin. It's the biggest impact basin on the moon. This is a topographic map of the moon. The center of the South Pole Aitken Basin, this is on the far side of the moon, by the way, near the South Pole. The center is about 8 kilometers below the average depth of the, or average radius of the moon, and then there are highlands near the equator of the moon beyond that. The entire diameter of the structure is about 2,600 kilometers. We think it's the it's the oldest recognizable impact structure on the moon, and we'd like to know, in this case, how much melt was produced and what role did melt play. To study that, well, we would like to also go sample it. This is done partly in proposal for a mission called Moonrise that was going to do just that. Okay. And you can see the red is melt, and it's pretty abundant. It forms a layer very deep beneath the basin and floods the surrounding terrain. You can see also, whoops, that the crust is thinned out in sort of a characteristic thinning and maybe respond to the rings and terraces that we see actually in the basin. This is the way we can explore the physics of what happens in such large impacts. Is by doing simulations of what we expect to occur, putting in everything that we know about what the impact should do, and then comparing it with observations. So the final conclusion is that, well, impact cratering is one of the most fundamental solar system processes, and it's a process that is at such a scale and involving such energy releases that the only practical means of study is by modeling, and I want to emphasize thoughtful computer modeling. You can't be sloppy about this or you mislead yourself. I'll stop there and take any questions.
Important reason for understanding crater formation better, which is that craters are our only real proxy for how intense the bombardments were early in the solar system. So all of our ideas about the energy flux and the spectrum of impactors in the late heavy bombardment come from our assumptions about scaling between crater size and the energy of the impact.
Yeah, the rather important scaling relations, the relation between the size and energy release are one of the first things we did computer models to validate. We've done now probably thousands of simulations with different conditions in both 2 dimensions and 3 dimensions to try to validate those scaling relations so that we can use them throughout a tremendous variety of sizes. Right now, one of the big questions is what is the role of curvature? If you have a planetary scale impact where the crater is as big as the object you struck, the standard scaling relations, which assume a planar target, and we're trying to come up with new variations that describe that. And in fact, a very contemporary aspect of that is the asteroid Vesta, which has a gigantic crater. The mountain on its south pole is the central peak of that crater, and the rim of the crater is at the equator of Vesta. Clearly, standard scaling relations do not work. But we're doing computer modeling to try to understand that, and are comparing it with what the Dawn mission, which is just now returning images, is finding. Actually, there's some mysteries there that are already intriguing.
There must be a class of problems that are very much like ones that have been solved and validated, and you know that the modeling is consistent with the physics pretty much. And then another end of the spectrum of the problems in which you're really extrapolating a lot. Is there any reasonable way to describe the boundary between those, and what would be ways for sort of pushing that boundary further outward?
If I understand you correctly, are you suggesting that computer models give you the means of extrapolating from one scale to another?
In any sort of modeling exercise, there are things you know you can validate in the lab or in the field, and some other things that are just further out there where you can't know what the characteristics of the impactor or the impactee. Where does your confidence limit go in terms of believing what you get out of the models?
I think it varies a lot. There are a lot of things we don't know and have to guess. For example, impacts, when we put in front of the crater, we do not separately know the impact velocity, size, and angle of impact. And we have to make up models that cover a range of those parameters to try to fit the observations. There are some things we probably never know. And maybe we'll make predictions. We're actually working with the students to actually getting a handle on now independently estimating the velocity of impact from something we never expected, and that is the size of the paper. So maybe we can by making these models make predictions of things that can be checked to give some of this additional information.
Was that your manner of speaking, or do you think it's because, I don't know, the problem is close enough to being understood that the resolution problem isn't fatal?
The problem, the major problem with the origin of the moon calculations is how much material that makes up the moon today came from the projectile and how much came from the Earth. All of the calculations that Robin has done suggest a preponderance of material from the projectile, not from the Earth, in the moon. However, every time she does a calculation at higher resolution, the proportion of projectile in the moon decreases. Probably won't. Well, and the issue riding there is that analytical techniques on oxygen isotopes and other isotope ratios have shown that the moon is isotopically identical to the Earth within very tiny error bars now. 10 years ago, this is not a problem, but the error bars on oxygen isotopes in particular have shrunk to the point that Earth and Moon are identical on the big delta oxygen plot, taking out the slope 1/2 for mass fractionation. And the Earth and Moon are different from everything else in the solar system. They're different from actual Mars, which would suggest that all of the material in the Moon came from the Earth. But the simulations, at most, give you 50% of the Moon is from the Earth. So we have a problem there. I've in other venues described this as a crisis of the origin of the Moon scenario. Unless we can resolve this, we may have to give up the giant impact. Hmm?
You mean literally resolve it. In other words, achieve high enough resolution.
I'm sorry, I didn't hear very well.
So we have to resolve it because, it moves to the Earth. Solve the problem of have high enough resolution.
Yeah, that's exactly right. Well, yeah. Well, from the modeling perspective, every simulation so far reported of the moon-forming impact has used the SPH method. And we know that there are serious problems with SPH. It is gives a very poor representation of mixing, which may be part of the problem. Maybe our idea of what the impacted Earth looked like is different. Everybody starts with a cold Earth. Maybe if it was molten at the time, we'd get more Earth vaporized and into orbit. There are many, many possibilities, but the first thing that's going on is that we're using modern 3D Eulerian hydrocodes to redo the calculation. The problem in these modern codes is putting in self-gravity. That has been done now in the context of 2 different codes, and the results are to be reported soon. Yeah.
Have to scan the angle of attack of the impact, the scale of the impactor, the velocity of impact, and so on. I mean, I would guess that, in trying to fit any specific stratigraphy, of the after effect, that you would also have to scan the mechanical properties of the substrate. And so my question is,
exactly.
How well do you think you're able to do on a priori grounds in fixing the mechanical properties of the substrate?
That's an ongoing process. The constitutive relations is a big deal, both within the defense community, where the effects of nuclear weapons are strongly dependent upon it, as well as potential hardened sites, and in the geologic community. At the moment, the constitutive relations that we're using, which derive to a large extent from static measurements, seem to be more or less adequate for explaining the observations. Some calculations I'm not showing you, but have been able to actually give very detailed pictures of how the stratigraphy in a central peak gets crumpled around, and we can compare that to observed central peaks and get pretty good agreement in its general details. But obviously we can go still further to finer and finer details, and that's an ongoing effort, which does not actually involve very many people or very much funding, but that's essential for resolving exactly what goes on. Again, it's a matter of what do you want to know, how much detail do you want, and what are you trying to fit. And for some purposes, it's not important. Yeah.
Detailed understanding of the mechanical properties of the substrate.
Jerry, you mentioned there of spatial scale and resolution. You did not mention much about the temporary scale. I guess everything goes very fast during impact, but there are some other process, such as melting and the transportation of sediments. So when you compare your model results with a geological profile where you see you are comparing with the strata and you were talking about sediments come back, do you have to worry about those processes that happens at a totally different time scale?
Yeah, everything I've been talking about today is on the short time scale of minutes or hours after the impact. Clearly, if you produce a large amount of melt, it crystallizes, it differentiates, which is something that probably happened in South Pole Aitken Basin, and the current models do not address that. Partly because these Eulerian models, the time stepping is controlled by the speed of sound, and you just can't afford to go to times of millions of years that way. On the other hand, you probably don't have to. What you need to do is apply another set of models that are implicit and do not involve the speed of sound as a limitation that will allow you to transport heat and look at isostasy and basically quasi-static type models. And so I guess what you're arguing is we really need a suite of models, not just one, that apply in different domains, because there is no such thing as a model that does everything. Lady in the back.
The sound is limiting, but doesn't Mercury model how much faster like the shock waves today, how much faster than the speed of sound?
I'm sorry.
I'm sorry. I've been suffering from a cold.
I was asking that during part of the impact, the shock waves, don't they go faster than the speed of sound? And do you not have to consider larger speeds than the speed of sound?
Yes. The shock waves do go faster than the speed of sound. And in fact, when we compute the time stepping within the context of the code, we use multiple criteria. We look at the speed of the fastest material. We look at the shock speed, although actually the speed of sound in the compressed region behind the shock is in fact faster than the shock. So if you use that as your limit, you already captured the shock wave speed. Yeah.
I was wondering how good are the mathematical techniques for analyzing the accuracy and convergence of SPH. It puts me in understanding why it's so low resolution and whether it can be fixed. The problems are very similar to something Andy might have worked on with discrete vortex representations, in which case, by using different kernels, you could actually improve the convergence.
As far as I understand it, I'm not an expert in this, but as far as I understand it, the standard means of estimating accuracy that are used for SPH work pretty well. And they say that SPH should give you a pretty good representation. It's only when you put everything together and compare it with either an Eulerian model or with an experiment that you realize that you have to use what seems like just an outrageous resolution or number of particles in SPH terminology to get the same answer. Willie Bentz and I years ago started doing that with an impact calculation, and he used a few thousand particles in his SPH code and it didn't agree at all. Then he used 10,000 and it didn't agree, and after using 1 million particles it agreed. And we said, well, that's crazy. He has to use something like 10 particles per linear size of cell to get similar resolution. That is, in 3D, you need something like 1,000 SPH particles per Eulerian cell to get comparable resolution. Somehow the standard models for what resolution ought to do and so on just don't capture that very well.
This class of problems is a beautiful combination of statistical mechanics, statistics.
Yes. I think like a lot of these things, the codes outrun our understanding of them. You know, you're making codes up on a kind of an experimental basis. You try something out like SBH, seems to work, and only afterwards does the strict analysis of the convergence and accuracy of the thing come along. It was years after Eulerian codes were developed that people, Rickmeyer and Morton, actually were able to analyze the accuracy of it. And things like AMR we still don't understand on a fundamental level. That'll come later. So to some extent, the modeling, I think, is empirical. Okay.
How does gravity affect the size of craters, and also the brittle behavior possible in the impact process?
Okay, well, as far as how does gravity affect craters, you know, gravity adds an extra energy that has to be supplied in order to simply excavate the crater. The initial excavation of the crater is not all that strongly controlled by gravity. The scaling relation is that the diameter goes as gravity to about the 1/6 power. So it's not really a big controlling influence on the crater size in excavation. In collapse and in issues that involve strength, it appears as the first power. So again, it matters. What matters is what do you want to know? Do you want to know when a crater collapses? Do you want to know how big it is? You know, our understanding of how gravity comes into this, what its role is, actually comes largely from, well, partly from the scaling, partly from analytical calculations. But we have to adjust the gravity to simulate these large craters. And what was your other question?
The other question that came in was, is brittle behavior possible in the impact process?
Oh, is brittle behavior? Yeah, we see that near the surface. Again, it has to be in a regime where the temperature of the rocks is low enough that you know, brittle fracture can occur. In the modern models, we have strength models such that we can actually see fractures and localization of slip zones. So this is a matter of getting the constitutive relations correctly. At greater depths in big planets, of course, the flow is ductile, and you don't see brittle fracture. But trying to simulate that transition correctly and apply that results is one of the frontiers right now, and most of the modern hydrocodes can do that. But it's a matter of as suggesting before, as Dick Peltier suggested, that you have to have the constitutive models that are capable of giving you brittle behavior in the right circumstances. So it's a matter of getting the constitutive relations to respect enough detail that you can show that. But we certainly see it in laboratory experiments, and we can do simulations now, say, of impact into a block of rock in the laboratory that show brittle fractures that look very much like what are observed. Okay, yes. Let's see, I think you asked, does the flow of material or the distribution of material cause a gravity signal with South Pole Aiken? We think so, and in fact, I'm one of the co-investigators of the GRAIL mission, which launched 2 weeks ago, that is designed to produce very high precision gravity missions, 1,000 times better than what we have now. And one of our aims is to better understand the distribution of mass in the South Pole Aiken Basin and compare it to these models. There's a mystery associated with these big basins that they seem to have positive mass anomalies in the center, similar to what have been recognized as mascons on the Moon for a long time. But even basins without mare fill have mascons. And it looks like the center of the basin is out of isostatic equilibrium, as if it somehow overshot and then froze with a mantle plug that is higher than you'd expect for isostatic equilibrium. We don't understand that. And that's something that's being actively researched right now.
I don't know if you heard the conversation late yesterday afternoon about one goal of a possible extension of the program here would be to bridge the gap between stochastic and deterministic models. Is that an issue for you? And are there other sort of mathematical developments that would help in understanding this problem?
Oh, absolutely. In fact, the old models for the origin of the Earth, going back to a model proposed by Harold Urey in 1952, envisaged the growth of the Earth as, well, imagine the Earth as a spherical cow, growing gradually with shells of mass added of infinitesimal thickness that just accumulate. Basically, it was an approximation of many, many small impacts adding to it in an onion shell fashion and growing the Earth gradually. That gives you a model of the Earth that's deterministic, that no matter how you grow the Earth based on that model, it has the same temperature profile. What we realize now with big impacts is that they are in fact stochastic, and we have impacts at every stage of growth of objects that are roughly half the size of a given growing planet. And the energy, the heat energy is added stochastically as a function of where the last impact occurred, how big it was, what its velocity was. And so we can no longer integrate up, say, a single model of the growing Earth. We have to integrate up a suite of models and then say, well, what's the most probable and what does the Earth look like? So the stochastic element is now a very important part of planetary growth. We just can't say what our actual Earth did. We can only say what a suite of models that kind of grew under the same conditions would have done, and try to figure out within that suite, where the Earth actually sits. And so that stochastic aspect is now a very important part of planetary growth. At the same time, we want to know what an individual impact with some well-defined parameters does. So, yeah, when I was listening to the discussion, I was thinking, we have exactly the same problem. We have deterministic models of an individual impact, but the growth of a planet, the evolution of all of our planets, is strongly governed by stochastic events.
Brings up another question. We have terrestrial planets and we have the major planets, and could the boundary between terrestrial and Jovian have been moved further out or in if the distribution of impacts had just been ever so slightly different? See my point? I mean, do you have some, can you think of this as bistability? There's one solution of the problem, which is a terrestrial planet, and another one, which is a Jovian planet, and depending precisely on this distribution of impacts that you were just mentioning now, could, Mars have wound up Jovian or Jupiter wound up terrestrial?
Well, it's clear now that
it's clear now that the orbits of all the planets are chaotic to some extent. We could lose Mercury sometime in the future, and Mars is not all that stable either. Looking at the integration. Back in the beginning of the solar system.
No, but I'm not talking now about orbits. I'm talking about the actual nature of the planet. It's a different problem for which I'm envisaging bistability. You see, not the orbital position or parameters in general, but the nature of the planet. Can it wind up solid with a hot core or liquid?
If Jupiter had only...
Does Jupiter have a rocky core?
It's believed that Jupiter has a rocky core, as well as a lot of ice that played a role in it. I think,
As you multiply the
you know,
number
as you multiply the number of players in the problem, the more deterministic it gets, or at least in averaging, the band of high probability becomes more and more prominent in directing the outcome. It's believed that when the major planets interacted with a disk of small particles, and those interactions depend more on the distribution of mass in the small particle disk than they do of the individual particles. But the models really haven't gotten to the stage that they can consider that these planetesimal disks that the major planets interacted with might actually have larger lumps and be planets in themselves. An idea that's recently been thrown out is that our solar system might have had another planet of Jovian mass that has since been ejected. And this sort of falls on the discovery that there are as many free-floating planets between stars as there seem to be planets around stars. So obviously during the planet formation process, ejection from the solar system is not uncommon. I expect we'll see models in the future trying to explain the planets with rogue planets that have since been thrown out. So, you know, we may be facing, you know, this stochastic element in the future.
Apropos of the question of where you were maneuvers, I don't think we have data on that. If 1,500 extrasolar planets, thousands more on the way. Build a catalog of where gas giants form, although right now the situation is when you look out at where planets are, you do see gas giants in close orbits, but that doesn't mean they formed there. The current theory is they formed farther out in a conventional way and then moved in. But as we get a bigger and bigger catalog, then by looking at age of systems and where the planets are, it may be possible to actually test these things against models.
Right, yeah. One of the current ideas coming out of the Sweary group is that the planets did a two-step, that Jupiter first moved in and then moved out again. That seems to explain some aspects of our solar system.
I'm wondering if we might want to move back to the bigger picture here.